My name is Jay Paul Agnes. It's very nice to meet you. I work for a nonprofit organization named FINRA. I'm one of the technology directors in Market Regulation Department. I've been with FINRA for the last 15 years or so, and for the last couple of years, I've been working on a cloud migration project where we move our huge portfolio of batch analytics that are currently running on MPP appliances, that's in FINRA's own data center, move that up to the cloud in a Hadoop platform into the Cloud Hadoop ecosystem. This talk for the next 30 minutes or so is really more like a real-world case study where we talk about our existing platform, the pain points that came with it, and how we address that with Hadoop ecosystem tools in the cloud, and the lessons we learned along the way and the benefits we reaped in the end. First, I want to go over a little about FINRA in general and the application that's undergoing migration before we dive into the more interesting aspects of Hadoop in the cloud. So what is FINRA? Most people don't know us. It's an acronym for Financial Industry Regulatory Authority. Oftentimes, we are called as Wall Street's watchdogs. What we do, our mission, our goal, our objective, is to maintain the integrity of the market and protect investors such as yourself who are buying and selling products in the securities industry, fixed income, and options markets. We do this by bringing in literally billions and billions of events. We bring in up to 75 billion events across different exchanges and financial markets in the US. Once we bring in this data, then we run our surveillances and processes on top of this data, trying to identify market manipulation, insider trading, as well as other violation activities. These violations can be very simple, like a traffic ticket type of violation, where we check to see if a firm reported a trade on time. Or it could be much more complex, where we try to see if someone is trying to tweak the stock price in the market. Once we identify these violations, then we enforce them. We have a variety of ways of doing that. We can basically fine them. We can disbar them. We can pull their license and take them out of the industry completely. And in cases of criminal matters, we do refer them to SEC to pursue. We saw about FINRA in general, and this particular talk is about a particular application within FINRA called as surveillance algorithms. This application has hundreds of algorithms that run against almost every exchange data across multiple products. These algorithms mainly look for abusive activities in the market and compliance breaches. You probably read about some of these practices like front running and spoofing before. We're trying to look out for you as an investor when we're trying to identify these violations. Our surveillances like best execution and order protection will mine the trade and order data to make sure that when you as a customer place an order, did you get the best price that was available in the market at that exact point of time? Front running will look to see if your broker placed an order ahead of you based on information from an analyst department before he actually shared that information with the customer, that's you. And then there's other manipulation techniques where they try to influence where the market is headed. They try things like layering and spoofing, where they try to show that there might be interest in the market, but it's actually not there, and they're trying to defraud the market in that regard. As you can see, we've been dealing with big data problems for many years now, and the problem has gotten only worse as the financial data kept getting bigger and bigger every year. Our surveillance application has over 400 batch analytics and has over hundreds and thousands of lines of code. Our legacy application relied heavily on the MPP appliances to solve our big data problems. Because clearly MPP was the leader in the big data solution before Hadoop matured into that space. MPP tries to solve the big data problems by partitioning the data across multiple nodes, and each node has its own local memory and processor, and the distributed nodes are tackled by a sophisticated centralized SQL engine, which is typically the brain of the appliance. Let's take a look at our legacy data architecture that was in place before we started adopting Hadoop in the cloud. We had a tiered storage design where the data was distributed based on specific retention period across these appliances. We had two main MPP appliance vendors. The first appliance is rather expensive because it had specialized hardware tuned to their SQL engines. The second appliance is a little less expensive because they had commodity hardware in the mix. Our design basically kept a limited data set, around a month's worth of data in the first appliance, and then close to a year's worth of data in the second appliance. And then as the data got rolled over after a year, it gets rolled over into the NAS and eventually into the tapes at the offline storage. As you can see, this design is trying to find a balance between cost, performance, and flexibility. Sure, we can try to buy the biggest appliance, number one, put all our data in it, run all our analytics on top of that data appliance, but that would mean that we shell out a lot of money on infrastructure cost. So instead, we tried to separate our analytics that rely on limited data set and channel them towards appliance number one. And the one that can run for longer period of time and that needs a longer date range, then we channel them against appliance number two. This helped us balance the cost and performance. And we were running in this model for many years. Although it's a good storage design, and we were able to make it work by trying to balance the cost with various other factors, we were still dealing with multiple pain points. The first and foremost is the data silos that came with it. Due to a tiered storage design, where data is physically distributed across these appliances, there is no one place in our system where we can run all our analytics for a wide range of dates. If you want to rerun for a date that's past a month, we need to rewire our analytics to run against appliance number two. And if you want to rerun for a date that's past a year, then we need to summon the tapes from offline storage, ship them, clear up some space in these appliances, restore them, revalidate them, and then run our appliances and the processes. This can at times take weeks to complete. The next obvious pain point is, of course, the cost. These appliances are not cheap. They are specialized hardware tuned for CPU and network performance. They have proprietary software running on them, forcing us to spend millions, and also indirectly resulting in a vendor lock-in. And lastly, the lack of elasticity. We are bound by the hardware in these appliances. It's not very straightforward to scale out very easily. To work successfully in this model, we need to constantly predict the growth of the data in the financial markets and plan our storage requirements well ahead for the coming months and years. If we don't plan well, we could either end up buying more or less capacity than we need, both causing us problems. Now let's take a look at how we address these pain points with the new Hadoop in the cloud architecture. This new cloud architecture, we use three main components to solve this. First is Hive, which is a de facto standard for Sql-on-hadoop. Then next is Amazon's EMR, which is a managed Hadoop framework which brings elasticity to Hadoop clusters in the cloud. And lastly, S3, which is a cloud storage solution provided by Amazon. We chose Hive as our main interface because we needed a Sql-on-hadoop solution. There are multiple reasons why we decided to stick to SQL instead of rewriting everything in a traditional Java MapReduce jobs. Primary reason is that we already have a heavily SQL-based application that are running on MPP appliances. And our source data set is already in a structured format supporting our Sql-on-hadoop route. That's hundreds of thousands of lines of legacy SQL code that was developed and iterated through the years. Porting that to Hive was a very easy win. And not only that, we already have a workforce that has strong SQL skills and the necessary business acumen. Giving up on SQL would also mean that we are missing out on all the talent that we've attracted and strengthened over the years. As I mentioned, Hive has become the de facto standard for Sql-on-hadoop. It has been around for 7 years and has reached a relatively stable state compared to other technologies that are out there. Although it's SQL, under the hood, depending on the backend engine, it's basically MapReduce jobs. It started with one execution backend called MapReduce, but now users have multiple backends for Hive. They can either choose Taze, Spark, or MapReduce, depending on the use case. Let's take a look at these different execution engines. First is our good old MapReduce framework. It's a very mature and reliable framework platform. In our experience, we found that it worked flawlessly and scaled well for terabytes worth of data, and I'm sure it can scale well for petabytes too. One downside, though, it's slower when you're dealing with queries that has many levels. Hive, behind the scenes, generates a chain of MapReduce jobs according to the query plan. And each job is independently responsible for completing one operation in that plan tree. And that obviously introduces delay in processing. That's the more batch-oriented nature of MapReduce. Taze was taken as a step towards solving the interactive query slowness problem. Taze tries to address some of the shortcomings we discussed with MR by trying to balance performance and throughput. For example, in MR mode, as I mentioned, Hive creates a chain of MapReduce jobs. And the MapReduce uses HDFS to store the temporary data between these MapReduce jobs, which is an overhead. Taze may try to solve it in a different way. It may create one map job with multiple reducer stage, allowing to stream the data from one process to another without actually using the HDFS, and which in turn will improve the performance. Lastly, the Spark engine. This is the new kid in the block. We haven't personally played with it much. We are looking forward to it. This was introduced only starting Hive version 1.1. And this engine is supposed to bring in all the benefits that come with traditional Spark framework, where it takes advantage of in-memory computing by fitting in all intermediate data in the memory and spilling back to disk only when it's necessary. The next important component in our architecture is Amazon's storage solution called S3, which stands for Simple Storage Service. This is a cost-effective solution that deals with just the storage. One of our architecture principles was to separate the storage and compute resources. That way, it will give us the benefit to scale out each of them independently as necessary. And Amazon's S3 fits that model very well. The other key feature is that S3 fits the Hadoop's file system requirements and works well as a storage layer for our third main component in our architecture, EMR. EMR, which stands for Elastic MapReduce, is a managed Hadoop framework that makes it easy to deploy and manage the Hadoop clusters in the cloud. It basically reduces the complexity of the time-consuming setup, management, and tuning of the Hadoop clusters and provides you a resizable cluster of Amazon's EC2 instances. These EC2 instances, which stands for Elastic Compute Instances, that Hadoop clusters run on are nothing but virtual Linux servers. There's a wide selection of virtual Linux servers that offer different combination of CPU, memory, and storage and networking capacity. Each of these server types include additional sizes to choose from as well. Say, for example, a compute-optimized storage instance called C3s come in 5 different sizes. It comes in large, XL, 2XL, 4XL, and 8XL instance. A large instance has 2 CPUs and 3.75 gigabytes of RAM, whereas an 8XL instance has 32 CPUs and 60 gigabytes of RAM. So there are different pricing models as well. You can either choose to operate in a spot pricing model where you name your own price and the servers get pulled out of you if someone outbids you. Or you can get the servers in an on-demand price where you get to hold on to the cluster as long as you need. So let's take a look at our overall cloud-based Hadoop architecture. As you can see, we fully operate within a logically isolated virtual network called VPC, or Virtual Private Cloud. We have our surveillance analytics here interacting with our management services that were built in-house and installed in persistent EC2 instances, which are nothing but a virtual Linux server, as I mentioned earlier. These homegrown services deal with workflow process management, data catalog services of all our source and output data that's available in S3, and cluster management services that interact with Amazon CLI for cluster provisioning. Every surveillance has a profile associated with it. That lets these services know about the instance type and the size needed for the job to complete. And our cluster management services here would then initiate requests to Amazon and spins up a clean cluster that's required to process this data. All our input data resides up here in Amazon S3, and cluster brings in the required data from S3 through Hive external tables to the local HDFS for further storing intermediate data set and further processing. And eventually, when the processing is complete, the output data is written back to S3. All our interactions to S3 happens through our data catalogs and services that's available here. It keeps track of every object, partition, version, and the corresponding location in S3. Once we publish our data output to S3, we have other applications here that provision the data in different formats to our end users here. Users consume the data either through plain old reports or through alert management system, which provides additional workflow and case management services on top of this data. We also collect and store application logs, billing data, and other information, and use Splunk and other tools to analyze that data to gain operational intelligence. This whole architecture has an underlying design pattern based on transient cluster with S3 acting as HDFS. In the pattern, the cluster lives just for the duration of the job, and both input and output data is completely stored in S3, and when you're done with your process, you basically shut down your cluster. HDFS is still used, but it's only used for temporary processing. And since you have the source data set available in S3, you can run multiple clusters against that same data set without overloading your HDFS nodes. There are multiple benefits in using this design pattern. You control your cost. You pay for the servers only for the time you use them. Since we have separated storage and compute separately, we don't need to pay for compute services as soon as the job is complete. Unlike a traditional Hadoop cluster, where the storage and compute are more tightly coupled. So you can lose one without the other. So although you're done using the job, you're still technically paying for it, although your job is not running. There's a very low maintenance. You basically start with a clean slate and you install the software on top of it. And when you're done using them, the cluster goes away. The other advantage of persisting data in S3 is that if you're working in the spot model that I mentioned earlier, where you name your own price, in instances where you lose your cluster due to an outbid, you can initiate reprocessing easily from the last point where you persist the data in S3. This is assuming you can take the hit on the extra processing delay. If you can, you may have to use the on-demand model. We went through some of the pain points and how that drove us towards a new cloud-based Hadoop architecture. For the next few slides, I'd like to go over some of the lessons we learned along the way during this migration exercise. First and foremost is designing your Hive analytics with focus on direct data access and maximizing resource utilization. Basically, the better the performance you need, the more you need to work for it. The objective in enabling direct data access for your process is to make sure that your process scans as little data as possible and still gets you the results that you need. You can do this in many levels. You can partition your data set in the natural query boundaries. This way you make sure that you hit the partitions, just the partitions that the process needs. For example, some of our processing is driven around when a trade was executed. So we partition our trade data set based on a trade date, and the process will hit just the data that we need and won't waste resources trying to scan millions and millions of rows. You can further bucket and sort the data ahead of time to enhance the join performances. Say, for example, you know a particular process that joins two data sets based on a particular join key, and the data set is huge, you're trying to improve the performance of it. You could basically bucket the data set based on the join key and further sort it if necessary. This way, we reduce the I/O scans significantly, and joins work much faster because the buckets are aligned against each other and a merge sort is applied on them. You can also use techniques like broadcast joins, where you publish the smaller dimension tables to all the nodes, and they're all held in memory and readily available for access. There are many ways you can maximize resource utilization in your cluster by tuning the Hive configurations. For example, Hive consumes data in chunks. You can adjust the min and max split size configuration to increase or decrease the number of mappers or reducers to take full advantage of all the containers that's available in your cluster. You can increase replication factor on smaller tables to make sure there are multiple copies, which in turn will increase your data locality and further accelerating the read operation. You can try to compress intermediate data that's transferred between mappers and reducers, which will improve the performance. The other thing we found is the importance of measuring and profiling your clusters from the very beginning and adjusting them continuously as your data size changes or the execution framework changes. As I mentioned earlier, there are so many types of virtual servers in varying strength and sizes available for you with the push of a button in the cloud. It's up to you to look at your use case and choose the type of the server that best suits you and the process configuration that fits your cluster. To prove this point, let's take a look at one of our Hive batch process and apply some of these instance choices and see how they compare against each other. In this particular process, it runs once a month. This is one of our processes. It consumes over 1 month of market order data, which is over 100 billion rows. That's roughly around 5 terabytes in size. As we saw earlier in our architecture diagram, we store our source data set in S3, and a cluster will access the data in S3 via Hive external tables and move only the necessary data into HDFS. Let's evaluate two main types of server families. First is a general purpose server, where a balance is established between compute power, memory, and network bandwidth. The second type is from C family instances, which is compute optimized, typically used for calculation-intensive applications that need more computing power. These are more expensive than M family, but they're more powerful as well. We ran this with 4 different settings. Option 1, which is we ran with a general purpose instance with 100 machines. Option 2, 3, and 4, we ran with compute optimized instances with 16, 32, and 100 machines respectively. So here are the results. As you can see, in row number 4 and 5, the cost and time factor, all of them ran taking its own different time, and each of them has a different price tag associated with it. The fastest, of course, is option number 4, where it ran with compute-optimized instance with 100 machines. But if you notice the cost in the preceding row, it costed around $312. The cheapest option is option number 1, which was running in cheaper general-purpose cluster with 100 machines. It cost, if you look at the row above that, it cost only $57. But at the same time, it took only 12 minutes more than the more expensive run. As you can imagine, option 1 seems like a good candidate if you're okay with that extra 12-minute processing delay, considering the benefit we reap on the cost side. I captured these numbers here mainly to show how important profiling your clusters and finding the right optimized setting for your cluster is more important. This is both on the cost front as well as on the performance side. All these were run with the same Hive settings. So there's potentially a lot more you can do by tailoring your split and memory settings according to the type and the size of the cluster. One of the easiest things you can do that can have big returns is abstracting the execution framework from your business logic. When we say execution framework, we mean the underlying backend engine, MapReduce, or Taze, or Spark. The underlying software in Hive, especially the ones with the newer framework like Taze and Spark, are constantly evolving. There's a great community momentum in these frameworks, and you may decide to go with MR, citing on its maturity than speed at this point of time, but you should constantly keep checking on these newer frameworks and adapt to it when the time is right. The next takeaway is about the flexibility we get with the Hive UDFs. I know I mentioned how great SQL is and how perfect it fits our application, but there are some instances when SQL did fall short. Hive user-defined functions are a great way to get around that. We've typically seen 2 types of shortcomings with Hive when we were migrating. First kind is a shortcoming in Hive SQL functionality compared to other SQL appliances that are out there. Say, for example, Windows functions in Netezza implementation of Postgres allows you to ignore nulls during the process, whereas Hive doesn't. So instead of trying to solve this using complex SQL, we wrote a Java UDF that can do the same thing. And you can call the Java UDF just like you call any other Hive function. Similarly, we found Hive did not have good date formatting functions like Oracle or other appliances. So we put together multiple Java UDFs that can convert formats in the way we like. And by the way, Hive 1.2 has good support for date conversion functions. The second type of shortcoming is when you're tackling a problem that's best suited to solve in a procedural way, meaning you find a need to iterate through your data set by holding temporary values in memory, etc. Say, for example, you have a data set and you want to dedupe by identifying completely unique pairs based on the time sequence in which you receive them. Solving that in SQL may not be very straightforward. You can write a Java or Python UDF and to resolve that outside of SQL and bring it back into SQL. Another takeaway when dealing with delimited flat files, either in HDFS or S3, is to do with choosing an optimal storage format and compression type. There are multiple formats you can store the underlying files that are accessed by Hive. Storage is typically either row-based or column-based. Row-based is where all the rows are continuously stored. Column-based is all the columns for a particular table are stored together. Columnar formats like Arc or Parquet typically perform better, mainly because when you run a Windows function on a limited number of columns, you enable skipping the unwanted columns. We mostly used Arc dataset in our application whenever we need a performance boost. But keep in mind though, if you are having the source dataset in a row-based text format, you need to run a process to convert that into an all-columnar format. And depending on how your infrastructure is set up, it may incur additional cost and time. The other factor is compression type. The primary benefit of using compression is the space you save in the disk. But it also means you're dealing with less data reading and writing, which in turn will improve the network bandwidth. There are many different compression algorithms that are supported, but they all have different pros and cons. Some are designed to be very fast. For example, Snappy here, the 4th in our table, is one of the fastest that's available out there. But they don't offer much in space savings when you compare them to the rest of the options. Some offer great space savings, but they're not as fast, or they may not be as splittable for Hadoop to split and distribute the workload. For example, gzip compression, which is the first in our table, offers the most space saving, but they're the slowest of the four, and they're not splittable either. So you need to choose a type that best fits your use case. And the final takeaway for the day is it's very cool being at the bleeding edge of Sql-on-hadoop, but at the same time, you need to be conscious of the fact that these are relatively new technologies, and you need to have the right strategy to mitigate risks and challenges that come with it. Hive, as such, came into play in 2008, and we started using Taze, which was just released in 2014, and Spark Engine were released earlier this year. But traditional platforms like Oracle were iterated and tested for close to 4 decades now. For open source software, the better the community momentum, the better the adoption. Typically, that means the quality of the software is better too. But if you still need to manage your expectation if you're coming from a traditional enterprise software background. In our migration effort, we did discover issues that were related to compression, storage types, and memory management. And our performance on interactive queries took a beating when we ran on MR mode compared to our MPP appliances. One of the main mitigation strategy we used was apples-to-apples comparison with the legacy output. We would run our migrated process for an extensive period of time, sometimes for 6 whole months, and compare that to the output in the legacy data that were produced for the same date range. This proved very effective in identifying issues instantly, and we had partnered with Hadoop and cloud vendors who could look at any code issues and provide us with a patch immediately. We also had automated regression test suites for every process that can be run with a push of a button. So we would rerun that test suite for any minor software increment to increase our confidence level before rolling out a change to production. Taze seemed to have addressed some of our interactive slowness, but we are currently evaluating Presto and other tools as well that were built ground up for interactive analysis. The other cool thing that came in handy with risk mitigation is cloud elasticity. Since we have these potentially unlimited number of servers at our disposal, we can kick off our parallel runs for 6 months or so in parallel, and we'll have the results ready for comparison in a few hours. This would have normally taken weeks and weeks in our legacy platform. So to sum up, the bet we made on Hadoop in the cloud has put us in an excellent position, helped us work around all the major pain points that we discussed during the beginning of the talk. We had good savings in infrastructure cost compared to a legacy architecture. We don't have to project market growth anymore and spend upfront buying heavy appliances based on our projections. We have a wide variety of machine types to choose from as well. We don't have to buy one big powerful appliance and share that across all our processes. Our infrastructure is much more dynamic. We can choose to run faster with better machines by changing a few configurations, or use a slower, cheaper machine if you're doing some tests based on smaller engineer data set. We don't have to deal much with software procurement or license management. Our cloud vendor deals with much of the heavy lifting there. We can run our prototype or data science type of runs without worrying about slowing down other processes that are running on production. We can scale out at will easily now. If it's a market-heavy day, we can decide that very morning that we need bigger clusters and apply that change quickly without any code deployments. And because we have more data in the cloud due to cheaper storage, there's no need to summon the tapes, restore them, revalidate them, and rerun them. We can initiate reprocessing immediately. On that high note, my talk is complete. Thank you for listening. Sure. Do we have any questions for Q&A? Sure. So we don't necessarily copy it. We have the data persistent in S3. So analytics will directly access in S3 via the cluster, and we bring in only the data that's necessary for further processing. So let's say there's a filter condition in a var class. So whatever applies to that var class, only that will be brought into HDFS. Not the entire data set, no. Yeah, that's. Yes, sir. Sorry, I couldn't hear you. I think there's a mic there if you want to get that.
Anything special we did to ensure security of the financial data?
I think I got the question. I think you asked if we did anything special to secure the financial data. Is that right? Yeah, so we have our app security group. That's the very first step that we took. They did full analysis on the cloud. So it's basically a combined effort. Both the cloud vendor as well as us, we both need to do it. So we have all these latest encryption, and sometimes we do our encryption, the key management on our data center instead of the cloud directly. So we have ways to protect that, yes. Yes, sir.
So when you said that they could cluster out and whenever you want to run, you are requesting a cluster to fail.
Yes.
How long that cluster will be time takes?
Yeah, so I think your question is when you request for a cluster, how long does it take to provision the clusters? So it depends on how many patches you apply. Typically, we've seen somewhere between 5 to 15 minutes. So around 10 minutes is the average, I would think. Yeah. Yes, sir.
What is your implementation of the catalog? As you talk about you have a catalog of data which you kind of important component of your
Yes, yes. So we took advantage of this migration to basically re-architect the whole data cataloging services. So we have a data management services which maintains all our data in the cloud in the enterprise. So we are actually in the process of making it open source as well. So we have a data cataloging services which are built off of REST APIs. It's completely built up of Java. So you basically call the API to register the data or to check if the data is available. So availability check, DDL services, and registration, all that is built into that service. Yes, yes, ma'am.
What's the maximum amount of volume that you process? And let's say the example that you mentioned
Yeah. So that particular process is a monthly process that consumes market order data for like 100 billion rows. That's a 5 terabytes. That's one process. We also have some processes that can run on 3 months worth of data or 6 months worth of data. We also have daily. So depending on the process itself, the size can differ. And we haven't seen any issues with scaling up or down so far. Yes, sir.
If you use a EMR, right? EMR always have some like couple versions data that's cloud data and distribution. Do you see that happen?
Yeah.
Or maybe also the question is the S3 performance acceptable? I mean, it's slower.
Yeah. So I think your first question was EMR up to date with Cloudera or other distributions that's out there? So typically that's a little bit slow. Like I said, we're waiting on Hive 1.2 at this point, which is expected shortly in a few weeks. That's because they do some optimization to work with S3. I mentioned S3 as a backend file system. So there needs some work. So there's a little bit of lag there. But typically, we haven't seen that impacting us much. And in terms of, you asked if the performance of S3, was it comparable to HDFS? Yeah, we did some analysis. It's pretty close. It's definitely not better than HDFS, but it's very close to HDFS performance. Yes, sir.
So what percentage is on-premise versus Amazon? And as you think about your roadmap, like where do you see that playing out over the next few years, 12, 25 years down the road?
Yeah. So we are part of a department, a market regulation department. Our goal is to basically completely move out of on-prem data center to the cloud by mid next year, 2016.
And there's no regulatory concerns around, data residency issues,
Yeah.
financial data.
So that's the first thing our CIO tackled. So that we made sure everything was still safe. We got all the approvals and everything was taken care of before that, before even we started doing the work. Yeah. Anything else? Yes, sir.
Have you experienced any data latency issues in moving data to the cloud?
So we don't. So we tend to operate fully in the cloud. So we don't have a case where we move data from a data center, our own data center, to the cloud, except for migration, where a one-time migration happens. So we have tools built around that to move the data from back and forth, but that will eventually go away once we move to the cloud eventually. Yeah. Yes, sir.
How do clients feels about QH moving data to S3? Because we definitely external data, in this case complaints is not originated by you, it's originated by us. How, like, the actual providers of the data feels about this?
I can't really answer that. We haven't heard any complaints, so I can't speak for the users as such. But if you want to address that,
Yeah, I can talk to that.
this is Brett, by the way. He's a senior director. He's my boss, actually.
Yeah, so before we took on this initiative, we made sure to front run all of this, no pun intended, with our various clients to make sure that they were comfortable with the data. And in fact, most of them already had initiatives of their own where they were storing a lot of the same data in the cloud. Even the SEC had initiatives going on where they were running some of their portfolio in the cloud. And back to the security issue, it's part of Amazon's core. This stuff has to be secure. They have a laundry list of certifications and external third parties that they come in and do audits on their security infrastructure. It's far more extensive than anything you can really build in-house. Everything lands encrypted, stays encrypted, and again, their audits and oversight of security on the Amazon side are almost more secure than anything you can build in-house. When we did our deep dive on that front, that is kind of where we landed. It's arguably more secure than what we had. And we had extensive security procedures already in place.
Anything else? Yes. Sir.
Moving the data from S3, loading in the EC2, this kind of sequential, isn't that 6 times to move the terabyte of data, loading, unloading? Because only in the normal cluster, we don't need to do that. Data lives there when we want the user to use it.
Yeah, so as I mentioned, we're not moving the entire data set. So what we do is we treat S3 as the HDFS layer behind the scenes. So consider HDFS and S3 are sitting parallel to each other. So we analyze that, we run our analytics directly on top of that data. So let's say if there's one query, the first query, if that can get all our results, we don't bring in any data into HDFS at all. So if there are multiple steps, with the first query's output is then not written back to S3 because we have HDFS in our service. So we just write it back to HDFS and then do a further processing. But that'll be a limited data set compared to the total S3.
Generally, like I have 10 years worth of data, I wanted to run some analytics and I wanted to do some reporting on that. So the way I'm writing a query of less than 25 times, which is like kind of common. Like excuse that, there's just no way. I can use some partitioning or bucketing kind of thing that I need this data, that data. But I want to run this query on all of my 10 years worth of data. Don't we need that 10 years worth of data loaded back to EC2?
No. So would you do that when you're actually acting on HDFS, if the data is stored in HDFS?
So the data is on the HDFS, yes, because it's a one view table, so there's a partition. I try to apply some partitioning on that just to make sure where I can improve that thing, so that when the query is coming from the BI to where the actually client try to see all the data, I don't have control. He can run, select all kind of thing.
Yeah.
So most of the scenario, I need that data to execute my query. I think that's fine. But the only problem is loading and unloading. I'm just wanting to share what's your experience on that.
Yeah. So this is more like not like a front-end interactive application or anything, right? These are batch-oriented application. We already tuned it to work on a specific partition, and we know how much of data is going to come into HDFS and all that. So S3 again is acting more or less like an HDFS. So there's no there is a bit of a performance impact when you directly run against S3 instead of HDFS, but that doesn't seem to be a major impact, especially on a batch-oriented mode. Yes, sir.
Hoping to solve problems they just couldn't do before, or do things in a new way. Do you have big plans for next year once they're fully resolved?
Yeah. So do you want to get that?
Yeah, that's a big. I think the first big effort is to get it all there, and I think we definitely see a lot of opportunity now to do things that we couldn't do before. The appetite to look back over years for an analytical study that just wasn't feasible before. It was a month or on our second tier of clients maybe a year, that type of thing. And we were always constrained by both CPU and disk. So at some point, we do production jobs, if we had a large analytics job to run, So the short answer is yes, and the long answer is we're still figuring out all the things that we can do now. That we basically have all the data there available to you. If it's longer than we keep in S3, if you push it to Glacier, you're able to get it back, and you have the capacity on demand. So if you're willing to pay for it, you can spin up more compute and do analytics and mining that you just do machine learning you just could do.
Are there some specific regulatory things that you're kind of thinking this is going to help you with?
It's again we're kind of just now getting into that, learning what we can't do or can do that we couldn't do before. But in general, I think the ability to mine and do machine learning on the data is far more enhanced than what we had before. So it's kind of a high general answers that we expect to be able to figure out some things that we couldn't figure out. Certainly, looking across instruments, that was very hard, if not impossible, in the legacy environment. You have all this options data, all this equities data. Now it's not as prohibitive to keep multiple copies of the data, so you can put a denormalized structure, look at the interactions between things you just couldn't detect before, just because of cost limitations, hardware limitations, storage limitations. So, I mean, that's the biggest place to look on for.
Yes, sir. I think you were first.
When you use Hive, do you use internal Hive table or external?
So the first interaction with S3, that happens via external tables. So that's where the gentleman asked about data cataloging services. So where we have all the schema registered with the data cataloging services, and the first access to the data in S3 happens via external table. And then after that, local managed tables, Hive managed tables.
So you need to build any specific layer of visualization on top of your Hive table, or direct on your table.
Did you say wish?
You need to build a report or something to annotate.
Yeah. So.
This is on Hive or on the client?
So it depends on the process. So these are batch processes, right? So some process produce the reports directly and emails it to the users via operations, or some would just put it into S3, and there are other alert management systems that would read directly from S3. So there are instances where we do build reports directly off of Hive, and we have custom framework code to do that, basically. Yeah.
When you process, do you use Hive or you use some other system like Pig or Java?
So we mostly use Hive at this point. So we're looking at Spark and other things for some other batch processes, but typically it's Hive, yeah. Thank you.